Saxon Advanced Mathematics, Lesson 31. Today's lesson may scramble your brains a little bit. There are no difficult calculations or lots and lots of steps to remember. It's not like that. It's just taking your brain and twisting it in a direction that might not feel familiar to you. But it's my job to try to step you through this. So let's see what I can do. The first word I want to make sure we are all talking about in the same way is the word symmetry. Symmetry is as simple as looking in the mirror. If we have a shape that we graph on our Cartesian coordinate system, it can be symmetrical. Symmetrical means basically that the shape can look across, for example, here's the x-axis, right? If this half of the shape looks across the x-axis and sees this half of the shape, it is seeing a reflection of itself in the mirror, right? That's the same. And in the same way, if the shape sees this as the mirror and this half looks across and sees this half, then it's symmetrical across the y-axis as well, right? So circles are lovely because they're symmetrical across the the x-axis, where x acts as the mirror, and they're symmetrical this way, where y acts as the mirror. All right? A line like this, where y equals x, is symmetrical in a different way. It's symmetrical across the origin, right? Because this looks across the origin and sees that. So it can be symmetrical, we say about, it sounds weird, but that's how we say it. A line or a shape can be symmetrical about the x-axis. That's what we showed in green. Or it can be symmetrical about the y-axis. And those are the main two we're going to talk about in this lesson. It can be symmetrical across the origin, but we're not going to talk about that as much. The first type of symmetry that we want to look at are called reflections. And I've already used that word, and I'm going to use it again in a similar way. Let's say that we have some parabolas. All right, and I'm going to start here. And we're not going to spend a lot of time graphing because we're going to get to that later. So right now I'm just going to draw them in and you can take my word for it. We've got a parabola that we're graphing. Here's the equation of it. Y equals x squared plus 8x plus 16. And when we graph it, it starts here. Let's see, this is minus 1, 2, 3, 4. That's minus 4. And it goes kind of like this. And here's the axis of symmetry, right? We've dabbled just a little bit in parabolas, and we know they look something like that. Now, if we want this parabola to look across the y-axis, right? It's reflecting about the y-axis, then it would see itself, right? Here's positive 4. It would see itself like this, wouldn't it? Pretend it's perfect. And this axis of symmetry would be at positive 4. What I'm going to tell you is that this equation would be the same, except every x would have a minus in it. Okay? So when we reflect about the y-axis, we did two things. We left the y value unchanged, and we replace every x with a minus x. See, that's what we did. The y's are exactly the same, but every x changes to a minus x. Okay? So this is the first rule that we're developing about reflections. If you want to flip it across the y-axis, to reflect about the y-axis, or across is another way we can say it, you take your original function and you leave the y exactly as it is, but you change the x's to minus x. By the way, if we started over here and reflected this way, it would work the same way. We just take negative x's and plug it in. All right, so that's the first rule that we developed. Now, what if we want to flip it up or down like so? If we want to reflect it across the x-axis. Let's look at that. So we're going to start with our same parabola that we had in the last one. It is y equals, x squared plus 8x plus 16. That's the same as what we had last time. And it started here at -4 and it went up. All right, this time, instead of moving it here across the x-axis, we want to flip it down. We want to reflect across the x-axis. So we want it to be like this, right? How do we make the numbers change to give us this? Well, this time, what we do, let me write you the equation. This time, we leave the x's unchanged and we put the minus in front of the y. And I'm going to write the rule just like I did last time. To reflect across the x-axis, we leave x unchanged Sorry, I ran out of room there. And we replace y with minus y. Okay, so the rule looks a lot like our other rule. Whichever axis you want to reflect across, you leave that variable the same and you put a minus sign in front of the other one. So that's the picture of this, right? Now, the difference is we don't like to have a minus sign over here. So what we're going to do is mentally multiply both sides by -1 to make that go away. And we're going to write it like this. Okay? Now, we're going to take these two rules that we just developed and we're going to write them in a slightly more succinct way. So, our rule for reflections. If we want to reflect across the y-axis, which was the first situation we had, we take whatever the original function was and we change the sign in front of the x. If we want to reflect across the x-axis, which again was this, we take the original function And this time we put the minus sign in front of the y. And then again by multiplying by -1 or dividing, however you want to think of it. We come up with this, okay? So what I want you to notice and to take great heed to is that we can apply a minus sign to a function in two different ways, either by putting it in front of the x's or by putting it in front of the y. And the way that it ends up looking is similar but different. If we want to change the x, then we put the minus sign right up against the x. If we want to change the y, then the minus sign ends up outside of the function, so to speak, right? It's not in the parentheses there. It's up here in front because it started like this. This is super important. This is what I want you to hold on to. These pictures that I've drawn up till now just hopefully help to illustrate and help you make sense of this. The most important thing I want you to take away, if you don't take away anything else, is that where we put the minus sign is very, very important. It makes the difference between a side-to-side flip or an up and down flip. And we're going to be using that rule in our problems, so we'll come back to this. Okay, those were reflections. That's where a function is looking at itself in the mirror, right? Now we're going to talk about a translation, which is a little different. Translations are when we're sliding things along a scale. So let's start by sliding them along the x-axis. And we're going to start with our first guy right here. And again, we're not going to worry about how we graph these. We'll get to that later in more detail. You already know how to graph a parabola. We learned that last year. We're going to say that this is y equals x squared plus 2. That's the name of this function. That's the picture. Okay? What if we want to take this very, very, very same parabola and we just want to slide it down this way? Let's say we want to take it down here to -8. We have to change this equation a little bit, don't we? We want it to be like this. Right here it was at 0. Here it's the same parabola. It hasn't flipped side to side or upside down or anything like that. It doesn't look the same, but it's supposed to be. What we do here, notice we're moving it to -8. So the way this equation is going to change is it's going to become y equals notice what we've done. I'm going to slide it up so I'm not in the shadow. We wanted to translate it 8 degrees toward the negative, so we add 8 directly to the x. Okay, pay attention to the way that we did that. It's kind of weird, right? What if we want to slide it in the other direction? Let's say we want to move it to +8. And again, we want it to look exactly the same. We don't want it flipping upside down or side to side or anything like that. We just want to move the whole thing down. Here we would use the equation y equals x minus 8 quantity squared plus 2. Notice that it's staying the same. We're just adding 8 to make it move this way and subtracting 8 to make it move this way. The sign is counterintuitive. You would have thought we would add 8 and subtract 8, but it doesn't work like that in the formula. We could do that. I could show you with the algebra why it works this way, but I don't want to clutter your mind with that. Right now, I want you just to trust me. So these are translations on the x-axis. Okay, we're sliding it up and down this way. And this is how we change our equation. To translate on the y-axis, So here's our y-axis. And again, we're going to start with our original point in the middle, or original function. That's in green. And this is y equals x squared plus 2. And let's say we want to move it up. Let's say we want to move it up 5 units. Okay, it's exactly the same shape. It doesn't look like it just the way I drew the picture, but pretend it's the same. What we're doing here is now we're adjusting the y-axis. We're moving it up 5, so we put the -5 there. And if we do the algebra, this will become y equals x squared plus 7. So this time we make our adjustment here. Again, a +5 yields a -5 here, but then when we do the algebra, we end up adding it over there. All right, so it seems like adjustments to the y-axis, the number moves in the same direction, right? We're adjusting with a positive number here. And technically we can see, oh, well, with the algebra, we started with a negative number over here, but then when we moved it to shove everything on the right side, it ended up being a positive. But that's kind of weird. It's different than this. And then if we want to move it down or in a negative direction, it would be y plus 5 equals x squared plus 2. And then we do the algebra and we get y equals x squared minus 3. So the way that we translate is to take the number of units we want it to move and the opposite sign, right, plus or minus, the opposite sign, and we adjust the variable that we're moving along the axis, right? So if we want to move along the x-axis, we go to the x in the equation and we move it the proper number of units, but with the opposite sign, right? If we're moving in the negative direction, we add it. If we're moving in the positive direction, we subtract it. That's more straightforward. When we go to the y-axis, it's more confusing because here we do the same thing. We want to move it up 5 units, so we subtract 5 from the y, but then algebraically we move it over. So it looks different after we adjust it. And then here we want to move it down, so we subtract. We're adding 5 because we want to move it 5 to the negative, counterintuitive, but then we do our algebra and it cleans up somewhat differently, and that is the confusing thing about it. So what we want to do is we want to take these rules and apply them to some problems. Once you get the hang of these, most students like them, but it does take a minute for your brain to kind of digest all the insanity that I just told you. Example 31.1. We have a picture. Let me see how many examples there are. 1, 2, 3. Okay, the graph of the equation y equals the square root of x. Okay, we have an equation. It looks like this. This is called y equals the square root of x. All right? There are a bunch of numbers on here, but I don't really need them. You can see it starts at the origin. Then John gives us another picture. It looks like this. And he wants us to figure out how we would write this function. Okay, so we have to take this one and adjust it for whatever's changing in the picture. So the first thing we have to do is, what's going on here? Are we reflecting or translating? Okay, well, we can see this thing has flipped around. It's like the mirror image of itself. So that means we're reflecting. So this is a reflection. Now, Did we go across the x-axis or the y-axis? So we look, well, where would the mirror be? It would be here, right? It would be on the y-axis. So it's the reflection on the y-axis. So that tells us when we're reflecting about either axis, we leave the variable that matches the axis alone, and we put a minus in front of the other letter. So we're reflecting on the y-axis, so we leave the y alone, and we put a minus sign directly in front of the other letter. So this is the name of this function. Okay? I did not rely on my notes to do this, but you certainly can flip back and look at this rule in particular and look at the examples that we did to help you get your head on straight. All right, let's try another one. We start with the same basic function. And John tells us, okay, this is, oh, I'm sorry, I'm using the wrong notation. Y equals the square root of x. But this time, he changed it up more. He went 3 units this way to -3, and then he went like that. Oh man, so what all did he do here? He reflected it down, okay, so shoot, I need another piece of paper. I ran out of space. He reflected it about the x-axis. Okay, we know that when you're reflecting, you take the original function, you leave the letter that matches to the axis the same, and you put a negative in front of the other letter. So that means we'll leave the x the same, and it'll become minus y equals the square root of x. And then we know that we clean that up by bumping the minus sign over. So that becomes y equals minus on the outside square root of x. Okay, now I have to go to the other page. Let me just quickly rewrite. 1, 2, 3, that's at -3, and it went like this. We started with f of x. No, we're not using that format, sorry. We're using y equals the square root of x, and we fixed it for the reflection, and we said it turned into y equals negative square root of x. That will get it to reflect down. Now we have to take into account this translation. It has moved 3 units across the x-axis to the negative. So what that means is we have to add 3 directly to the x. So we get y equals negative square root of x plus 3. This sign is always wonky. We adjust it on the axis where we found it. This is our final answer. Okay, so this was how we adjusted for our reflection. And this is how we adjusted for our translation. Okay, and then this next one is going to be the craziest of all. We're going to put several different pieces together. So let me draw you some pictures. Graph the equation y equals 1 over x. Then write the equation of the graph that has the same shape but is translated 3 units to the left and 4 units down. Okay, so we have to make those 2 changes to it. All right, the first thing is, how in the heck do we even graph this? Well, you could just make a chart and plot it out, but I'm going to tell you right now, this is the reciprocal function or the reverse function of, yeah, it's a reciprocal function. So what I'm gonna do is I'm gonna start by drawing y equals x, like so. This is y equals x. Then I know at the point 1, 1 and minus 1, minus 1, that's where we have these asymptotes, right? This is how you graph this thing. Remember we talked about this briefly? And I said it's kind of a weird thing, but you just remember it and do it. So this is the graph of y equals 1 over x. This is the one I'm interested in. Okay? The line just helped me find this. But this darker one is the one we're interested in. Now, what we have to do is we have to shift it. The whole thing, we have to shift 3 units this way, 3 units to the left, and then we have to shift it 4 units down. We don't necessarily have to draw the picture of it, but we have to write the equation. So, this 3 units, this is shifting along the x-axis, and the 4 is shifting along the y-axis. Okay, so I'm just keeping straight which axis is moving how many units. Now I can take my original function of y, and I'm adjusting 4 units negative, right? I'm going down 4, so that means I need to add 4 to the y equals, and then it's 1 over, because that's just the way my basic function is. And here's my x, and I'm moving 3 to the negative on that. So again, counterintuitive, I use the opposite sign. So I adjust there, okay? So here are my 2 adjustments, and here's the way I show them in my formula. And now my last step is simply to subtract this minus 4 because we want the y to be by itself. So my final answer is the function, this function shifted in these 2 ways, the way we were told to do it. The final answer is y equals 1 over x plus 3 minus 4. That cancels, and that is what I'm left with, right? And so this is my final answer. That's a little mind-blowing. That's a little trippy. If right now you feel like this is gonna make you rip all the hair out of your head and scream, I understand that. Just use the basic rules that we talked about. Use the notes. Pay attention to the weird rules. I didn't even try to write them in words because it's just weird. But use these rules to slowly work your way through this and make the changes that they talk about. Good luck. Thank you. Goodbye.